the windows.
Last week.
I refuse to have a Mac, so you can help me to. Oh.
I have my slide.
Okay. So here I'm going to present to you the basic idea of this minimal zk virtual machine that we are trying to build in order to aggregate those XMSS signatures. So first, as explained, the goal is to be able to aggregate XMSS signatures, and second, to be able to aggregate those already aggregated signatures, so to have recursion in the end. And to do so, there are a lot of good ideas that we can take from Kero, and here the thesis will be to limit as much as possible the use of precompiles in order to keep it as simple as possible. To give you a brief overview of a current potential idea of how such a VM could be implemented, here is a proposal where you have one read-only memory, as in Kero, two registers, frame pointer and program counter. The difference with Kero is that you don't have the AP, the allocation pointer register, and I will explain later how to do it, like how to make it work without this register. And so you have one memory which is committed. You can see as like a big chunk of field elements in the base field, and you have a byte code, and at each cycle you execute one instruction that will read and like fetch some elements in memory, assert some equality like add and mul constraints between the elements in memory, and you can also have jumps and the reference, as I will explain next. There are four basic instructions. Like it has been designed to be as simple as possible here. So as explained, you can add and multiply elements in memory, but the index in memory that you access are relative to FP. So FP is the frame pointer. It points to the start of the current stack or the current frame in memory that you are located at. And you can also multiply, obviously, feed elements. There is this dereference opcode that allows you to, as its name suggests, dereference some kind of pointer, and this will be useful to access elements in memory that are not in the current frame. We'll see later why it's necessary. And finally, a conditional jump, which basically lets you jump at a different location in the bytecode based on some condition. And when you jump, you can update or not the frame pointer. Because the two operations we are trying to verify, first XMSS aggregation and second recursion, heavily relies on hashes, we will naturally need some precompiles, and obviously two Poseidon precompiles, Poseidon over the Poseidon permutation over 16 and respectively over 24 feed elements. And there are also 2 more precompiles that have been found useful when implementing the WIR recursion algorithm. But this is like just a detail. More importantly, you can focus on those 2 precompiles that basically let you perform Poseidons over feed elements in the memory. Here is a quick overview of the proof system, how it has been designed. Contrary to Cairo, we are in the multilinear world. Everything is a multilinear polynomial. The field, as explained, is Koala-Bear, and the extension degree if you accept the conjecture up to capacity, you can get close to 128 bits of security with some grinding, and an extension degree of 5. It works. And so the PCS is WIR, and you replace like everything, almost all the machinery in the IOP is based on some checks. So, for instance, to prove errors, you don't use the traditional quotienting technique. You use a sum check, like a 0 check, to prove the validity of your error tables. And using this sum check based approach, you also avoid to commit to the quotient polynomial, so you can gain a bit in terms of commitment. So with sum check, you can prove validity of those different tables. Basically, there is one table for execution. Like this is where every cycle in the execution of the VM corresponds to one row of this error table. And then you have some tables for the precompiles, and then you have your memory. Here, not everything is committed. The memory is committed except for the public memory, which is the part on which prover and verifier agree. It's the part of memory which is useful to pass like the arguments to the program you are trying to verify. For instance, in our case, the message and the public keys of the XMSS signatures. And you prove the consistency using 2 things. First, a lookup. For instance, in the execution table, we have a closer look later, but some columns are in yellow are not committed, thanks to lookup star, which is a recent indexed lookup by Lev Sukhanov, which allows you to only, for instance, here, this indexes column are index that will point to memory. For instance, if the index is 4 here, it means that the 5th element in memory should be stored at the corresponding value here. But traditionally, what you would do is that you commit to the index, you commit to the table which is being accessed, and you also commit to the resulting data. But with lookup star, you can skip this commitment, and those columns become virtual columns. When it comes to the lookup from the execution table into the memory, you will not gain a lot. Actually, in our case, there are approximately 3 times more indexes that there are cells in the memory. And if you do the math, if you compare the commitment cost to lookup versus lookup star, it's similar. Because in lookup star, you avoid committing to the data, you avoid committing to the accumulation, but you have to commit to the push forward of the equality kernel. So the cost here is similar to lookup, but the great advantages appear when it comes to the bytecode. Because in this ZK virtual machine, each instruction, it's the same in Cairo, is encoded, you can think, between 15 to 20 flags and operands. Each instruction is encoded, for instance, there is a flag, is this instruction an add? Is there is a flag if it's a mul, 0 or 1, etc., etc. And so at each cycle, you need to fetch those flags, and you can interpret this operation of fetching the corresponding flags and offsets and the shifts, etc., from an indexed lookup with the PC column program counter into the bytecode. And this operation can be performed extremely efficiently thanks to logupstar, because you avoid committing to those 15 or 20 columns representing your flags. They become virtual columns. And in the end, you also have some grand product GKR thing to prove the overall consistency between the precompiled call, because each time you call precompile, you need to ensure that it appears indeed in the Poseidon 16 table. And here, as explained, thanks to logupstar, do not commit to the data which is accessed by an indexed lookup. So in this part, you will not gain a lot versus the classical lookup, but here in this part, when it comes to the bytecode, you gain a lot. And in the end, the execution table is mostly composed of virtual columns. You only commit in the execution table to PC, FP, and 3 indexes column. So you only commit to 5 small field elements per cycle in the execution table. You need to commit to other stuff, memory, etc. But if we only consider the execution table, it's very lightweight in terms of commitment. And quickly, to give you an idea how we can use those 4 basic opcodes to do interesting and useful stuff. Here is an example of how to implement some kind of functions with this very primitive ISA. Imagine you are here, so this is your current frame or stack in memory, and you want to call a function, my function, with input y. You must know in advance the memory footprint of the function, and you also know, obviously, the location in the bytecode of the function. Then what you do is that instead of relying on the AP allocation pointer register, you will receive as a hint the location of a new frame in memory, which the prover that runs, that is trying to generate the proof, has access to, knows which part of the memory is still free to use. So the prover can allocate some memory, knowing how much memory is required, and the prover will hint by inserting here the location of this allocated memory. And then the program will jump to the correct, to the location, like there is at the same time a jump in the bytecode, to jump to the function, and you will update the FP register with this hinted value. So in the bytecode, you jump to your function, and in the memory, your FP jump to this new value of FP. And the key idea is that because the prover has the liberty to put the chunk of memory wherever he wants. The key idea is that because we are in a read-only memory, there is no risk of overwriting previous memory with this chunk. So the prover has no choice to allocate a free space of memory to put it, to place this new allocated frame. So the prover cannot cheat, because it would obviously not work at all if we were using a read-write memory. In the end, you execute the bytecode of this function, and one important thing is that using the dereference instruction, that the deref that allows you to write stuff. Basically, the deref allows you, when you are still, before jumping, you are still in this frame, you are able to write the value of the input of your function in the newly allocated frame. You can also write the value of the current frame pointer here, and you can also write the value of the current program pointer in this new frame. Then you jump, and at the end of the execution of this function, you will be able to jump back to your previous context using those values PC and FP that have been stored at the beginning of the newly allocated frame. And this mechanism allows you to have functions even though you don't have the IP register. And using this, you can have loops because you can transform your loops into your loops into recursive functions. And basically, you can do whatever you want. Like it's sufficiently general to write a complex program. And one last thing I wanted to point out is that recently Dimitri found a way to use the dereference instruction, because as you can see here, the memory will be accessed with some value, some index, and this will not work if the index is bigger than the memory size. And using this fact, you can have a check that some value is smaller than the size of your memory. And if you know that x is smaller than the size of the memory, and you know that, let's say, 10 minus x is also smaller than the size of memory, you know that x is smaller than 11. And basically, in 3 cycles, this is not an intended consequence, but you can, it's funny, but you can use the deref instruction to perform efficient range checks in only 3 cycles of the virtual machine. And to conclude, the main things that remain to be done is to fully implement the recursion program. Only WIR has been implemented for now. To implement properly the XMSS program with the appropriate encoding, but this is one of the important topics of this workshop. And finally, to improve performance, even if performance has been improved over the last weeks, we still need something like a 5x to have like a good performance. And there are still quite a bunch of known optimizations that are not implemented yet. So we should be able to at least land close to the performance targets. Thank you.
That performance is single-threaded or using?
It's yes, it's multi-threaded, but it's on a CPU. Everything here is the performance is on a CPU on this machine.
So according to the figuring that you presented yesterday, there would be maybe about a 12% improvement in the efficiency of the consistency check between the memory table and the execution table, were we to use logup instead of logup star for that. So is that accurate? And if so, what is the reason for using logup star for that?
The reason is that indeed maybe logup could be slightly more efficient when it comes to the lookup. Sorry. Yes. For this lookup, execution to memory, logup would likely would be slightly more efficient. The reason is to use lookup star is just by simplicity to have only one lookup argument, I would say. Because if lookup star is much more efficient for the other parts, why not use lookup star everywhere? But I believe if the number of indexes is 3 times the size of your table and the extension degree is 4, lookup star is almost as efficient as lookup. If the extension is 5, lookup star is slightly like maybe 12% less efficient.
Thank
Thank you. Thanks a lot for this. So I have a couple of questions about, so my understanding is that you designed the opcodes from the ground up. So I have a couple of questions, a little bit about the opcodes chosen. So the first question I have is, is this the minimal set of opcodes you need for Turing completeness or full expressivity of your language? And secondly, so I noticed you have deref and jump in there as fundamental opcodes, which to me strike me more as, in a sense, helper functions for navigating memory.
Yes.
So I was just wondering, especially given that the Lean ISA is fundamentally motivated by your need to verify a very specific structure, right? So the Merkle tree with all the paths, I was just wondering if it would just make your life a lot easier if you enforced a specific structure for your memory, for example, a binary tree, so that you get rid of some of these, and you don't have to worry about the kind of overflows and all of that really nasty stuff, and therefore sort of like still keep the expressivity by keeping, for example, addition, and probably you also like latently have equality as another opcode, I presume.
Actually, you can do equality by addition with 0.
Okay, sure, yeah. And so in a sense, if you really just only need that for Turing completeness, and the things that you particularly care about have to do with the very specific binary tree structure, maybe things are just much easier if your memory is indexed like that as well.
Actually, what you're suggesting, for instance, if we only keep add and null, it's an arithmetic circuit, but it would be totally doable, I guess, to implement the XMSS aggregation with a custom circuit. Like it's doable. The hard part, I believe, is for the recursion, because you have to do your recursion recursive circuit. You could also imagine to have a recursive, like the recursion being done with a complete circuit, but the idea is that I believe it's simpler to use a minimal zkVM.
I agree with you. I guess what I'm saying is that instead of giving full control to your compiler or to your ISA to reach any part of memory, which I don't personally, that scares me, you just have one index sort of lookup function, which basically would say something like, look at this part of the tree, instead of having derefs and jumps, and then just run through with your custom ISA, so with your addmul and whatever else you need that's very cheap and 1 or 2 constraints to do in the transition. And every time you need access to memory, you just run that opcode, and what it does is it just does a sort of, in a sense, a Merkle lookup into your memory trace in which you've enforced that you just have very specific places you can put things. And you can even just adapt this to still be general, but have like the XMSS structure that you need as fitting in very nicely. I don't know, I'm just spitballing.
So instead of a continuous memory, to have a more granular memory adapted to our problem?
Sort of. I mean, I still want to keep generality, but what I'm saying is, so your memory basically is like a big block, and you can go anywhere, right? And that gives you a massive amount of freedom, and it sort of reminds me of what most compiler languages look like. What I'm saying is, in a sense, instead of your memory just being from 0 to k, like in every bit, I guess it's a field element with a certain number of bits, instead of that, you just index it differently. So the way that you index it would be something that is very cheap for you to sort of instantiate in an opcode, so that, for example, when you're doing your signatures and you need to make sure that all the different parts work out, so basically abstract away the refs, derefs, and jumps, because you get generalization, right? But my argument is that you can probably get that by making more structure there, just to make your life easier, honestly.
this is exactly the kind of conversation that we want to
Sorry, I
have
got really excited.
during the workshop. This is great.
It's interesting, yeah, it's interesting.
And this relates to the work that you wrote about, right?
Yeah.
For the NockVM and all of that stuff. Yeah, for sure. Let's have this conversation. We have 2 more questions. Oh, 3 more questions. 4 more questions. Okay, let's be very quick.
Thank you for the talk. I want to ask, is it possible to use this leanVM for other applications? For instance, for recursion in like zkVMs, for like writing verifiers.
I guess yes. Everything hash-based should work.
I see. Thank you.
Hi. So for the, I understand we will want to formally verify the recursion program and signature aggregation program and the signature program, but will we also formally verify the ISA itself?
Alex said yes, so the answer is yes.
Thank you, Mel. If I understand correctly, when we write a program in this language, it's then compiled into like a circuit or something. And you mentioned as an example that if you supply wrong parameters into DREF, the program should fail. So that if, when you compile, it means that you provide some additional sanitizing checks for the inputs. I wonder, in general, when you compile the program into the circuit, which kind of guarantees it can provide, which kind of sanitizing checks it gives to the prover and verifier.
Not sure to you mean when you compile from the high-level DSL to those 4 opcodes?
No, from the opcodes, you obtain immediately, like, how to formulate it, a circuit or like an A or whatever. But it doesn't accept any input that thing. You say like some inputs would fail because they are out of memory or something, and they wonder if like a general set of
Yeah, okay. Actually, there are some air constraints that at the execution table here, you have it's similar to Kero. You have some like 10 to 15 air constraints that will say if it's an add, I want this to be the result of this addition. If it's a null, I want this to be the result of this multiplication. And you have some, and if it's a jump with condition to FP, like I want to change FP, and you have a bunch of constraints that ensure that the intuition, of the opcodes is sound at the level of the proving system. But actually, your idea about the DREF, it works because there is an indexed lookup from the execution table to the memory. And this is this lookup that would fail if you try to index with something bigger than the memory.
Last question. Your mic might be muted. The bottom.
Yes. So currently,
thank you. Currently, do you have estimates on how much of the time does the lookup, the lookup star argument take? And did you look at alternatives, say recent memory arguments like twist and shout?
Currently, lookup star is a significant portion. Even though yesterday there was some interesting idea, I think this should be reduced in the coming days. Still, lookup star is a significant portion. About twist and shout, I'm not an expert, but my understanding is that those memory arguments require to commit to a bunch of ones and zero, which is perfectly suited when you have elliptic curve commitments or binary fields commitments, because it's quite cheap. But if, in our case, you commit your ones and zero interpreted as koala bear field elements, I guess you will have some big overhead.
Yeah, but I think it can be adapted. We can talk later.
Okay.
Perfect. Thank you so much, Emil.